The screen is shared. Just check on the mobile. Everybody. All right. So let us continue. Now I would be dealing about the parallelism that comes at various levels. Some of them, some of it is exposed to the programmer, some of it is internal to hardware. That which is related to hardware, I will go through quickly because that is just for your academic interest. Maybe you are already aware of it, or doesn't matter if you don't understand it in beginning. But the one that is exposed to you, I will try to cover it in detail. Alright, so there are some abstraction layers, and at every layer there is some parallelism. So starting with somebody was asking about the execution unit, how they are. So there is above that there is a microarchitecture, and microarchitecture is actually the interface. These two things are in the hardware, and this is the interface that is the instruction set architecture. Is the interface between the software and the hardware. So ISA as they call it, like Intel x86 is an ISA. So any program that was written for 80386, which was i32, can run on today's computers. So that is, however, what is written for today's i7, i5, that may not run on that because instructions got added later. But the base architecture is called as i32. Then comes on that the operating system is the next layer. On top of that, then your application program. So typically, you have a hardware and the software. The hardware, as we see, is the motherboard that you saw, and the OS loads on it from the hard disk, and then you run the application program. So that is the model that you already know. So now at every level, there is some kind of parallelism that you see. So, no, it is a specification. Instruction set, list of instructions. So actually, ISA itself is a big topic to discuss, which I mean, at this point, just remember that every CPU has a set of instructions, and that defines what the CPU can at this point as ISA. So in the execution unit, there is something called as pipelining. I will briefly touch upon it, not very relevant to you possibly, but good to know. The microarchitecture, there is something called as superscalar. It is more than one processor execution unit exists there. I will explain that. Then single instruction, multiple data, that is achieved through a set of instruction. I will explain that. Then the operating system manages multiple processors. We saw two of them, and multi-core. That is, every processor has got multiple cores. So I will explain how that works. And finally, at that, this is what should be of interest to you if you are writing codes. So if you are writing code, you have to look at this parallel programming frameworks and how you can take advantage of the sibling. So there are frameworks that are available for that. Rest of the things is typically transparent to the program. So let's look at how pipelining works. So before that, typically you have an arithmetic logic unit, which is the heart of that CPU, where arithmetic and logic instructions are executed. So you have a set of instructions, and so this is like, but you can see this sequence: first, second, third, fourth, fifth. Like this, the instructions are entering, and every instruction has its got data. Like the instruction, suppose is add a comma b, and add enters from here. The data is in register A and B, and you get the result. That is addition of two numbers. Okay? So So if A contains 2 and B contains 2, the result is 4. So that is a basic way. So similarly, add, subtract, multiply, all sorts of. Similarly, this is integer. You will have a ALU. Similarly, your FPU, floating point unit, which will become floating point operations. So this is the basic thing that you will find in any processor. Even if you have a processor in this remote control that I have, there is a CPU inside this that also works on the same model. Supercomputer also works on the same. So now, if this is to be used, this ALU is to be used, what we saw that there are instructions that are operating on a data, then there is something called as, typically it will be divided into 4 cycles. What are those 4 cycles? First is fetch the instruction, which will then be decoded. After decoding, you will know what are the operands. The operands will be brought in. Then it will be executed. So fetch means add is fetched, add a comma b is fetched. Decode means it is add is to be done. On what? It is to be done on A and B. In execute, you will add the two numbers and the result will be stored to the destination, to the memory of the register. So this is what a typical works. So not necessarily all processors do not use this, but this is the basic one that every processor will have. They may have more, they can divide this into more, but this is the bare minimum. So this is the way it works. Like in first cycle, the instruction is fetched. Second cycle, it is decoded. Third cycle, it is executed, and fourth cycle, it is written. So there are different units doing this. There is a fetch unit, there is a decode unit, there is execute unit. What is execute unit? I showed ALU is the execute, and the data goes back in the memory, right? So, but instruction will take 4 cycles. So, if you have a non-pipeline architecture, what will happen is 2 instruction will take 8 cycles, 3 instruction will take 12 cycles. Like this, it will go. However, starting with 8085, that was made for many of you were even born, they are using what is called as pipeline. So what we do is, instead of having it disjoint like this, we will try to overlap. Okay. So let us see how it happens. So same thing. Instruction 1 in first cycle is fetched. What is going to happen in T2? It is going to be after fetch decoded. But at the same cycle, you can now fetch unit is not being used, so it can be used for fetching item. In T3, it is going to be executed, but the fetch and decode units are free. So it is going to, the instruction that was fetched in the previous cycle will be decoded here, and the fetch unit will get heard. So like this, it will continue, and you will find that in the 6th cycle, all 3 instructions have been executed. But what I have not shown is the next instructions are fetched, decoded. Like this, what we have found is these which were 4 plus 4 plus 4 now have shifted towards your left. Okay, and they got, now what happens is every unit is busy in every cycle. As a result, what is that we got? This was the 3 cycle initial delay, but on 4th cycle, every clock you are getting an instruction completed, right? In the previous case, every 4th cycle one instruction was getting completed. Now you have a delay of, so each instruction is still taking 4 cycles, but by overlapping this, we are able to make the instruction effectively execute every 1 cycle if you can ignore this. However, in this case, what happens is how many instructions are parallelly. So 4 instructions are in some state of execution, but they are still taking 4 cycles to complete. But there are hazards. Like if there is a jump instruction, if there is a, suppose there is a jump instruction at 200, says jump to 300. That means 200 says jump to 300. So 201, 202, 203, which are entered, they have to be thrown away. You have to again start. So there is what is called as a bubble in the pipeline. So don't worry about that. What we are trying to say is that this will go on smoothly, provided you are executing 100, 1, 2, 3, 4, 5, 6, 7. But no program is like that. You will have loops. You will have conditional jumps. So that is the way pipelining works. Okay. So now coming to the next part, we said that execution units are superscalar. What does it mean? Now this unit we know pipeline execution unit that is already having parallelism. So instead of one unit, you have two such units. So what's happening is that the instructions earlier, I1, I2, I3, I4, I5, they were all going, sorry, they were all going on the, they were entering I1, I2, I3 like this, I4 goes here, I3 is like this, they were, I1 was here, I2 is here, I3 is here, I4 is here, like that they were going in a row, like you are standing the queue for the tea. One person takes tea, so you are fetch, no decode, but there is an execute where you get a cup of tea. So that is what that pipeline execution unit is. Now here, two such units are here. That means what can theoretically happen is, see this is all same fetch decode, but issue you can have two units. I1 goes here, I1 enters here, I2 enters here, I3 enters here, I4 enters here. So if possible, I am saying if possible because I'm not working on dependencies. There could be, what is happening is that effectively you are executing two instructions in one flow. What was happening? One instruction. If you have four such units, four instructions. So this is theoretical peak. It may not always happen because it's like this, that I1, I2, I3 they are order coming in. So I1 goes here, I2 goes here, I3 goes here. So it's a best case scenario. In practice, it's possible that result of I2 is needed by I3. So I3 cannot go in unless I2 is done. So those are called as, there are data hazards, data dependencies, control dependencies. We will not get to that. But now this parallelism is done by the hardware. Pipelining is done by the hardware. So user has no control. Why are they doing it? You may have seen that earlier Intel processors, they used to work at 40 megahertz, then 160 megahertz, then 1 gigahertz, 2 gigahertz. So how was it happen? These such kind of things, increasing the pipeline width, depth, increasing the number of execution unit. These were done by Intel, so it's internal to it. Program still remains same. Whatever was running on a non-pipelined, non-superscalar architecture will still run here as it is. User doesn't have to do anything. Alright. So this you can, if you are not interested, you can ignore this because that is transferred to the program. However, this is what you should understand. This is in the instruction set. Okay? Single instruction multiple data. That is what GPU uses. Okay? The whole purpose of GPU is this. So I will talk more about it later. So this is useful for algorithms that can take advantage of it. So there are certain algorithms where the data set is huge, but the instruction that you want to operate is the same. Like I will show it in the next slide how it works. So this is called as same instruction but multiple data. So this was introduced by Intel and AMD. So earlier instruction set did not have it, but subsequently have it. So there is something called as AVX 512. So I will show you how this works, how it packs in the next slide. Point is to be noted is there are some workloads where there is streaming data, like audio, video, or a set of deep learning, these kind of things, where let's say MPEG-3 encoding, you have a stream of data coming. Data is same, but the data is varying, but the transformations are same. So it's like a pipeline through which the data is processing. So the instructions are agnostic to data. Whatever data comes, I could have one instruction operating on one data. But if the same instruction keeps, I will show in the next slide, I think I should show you that. So this again, same thing. Now suppose you want to, you have a streaming data on this processor like this. What will you do? You add A0 with B0 to get C0, one instruction. Next instruction, A1 with B1 to get C0. So there are three instructions that are executed in a loop. One takes A1, A0, other takes B1, third takes A2, with B0, B1 and B2 and produces the result. Now, how does SIMD work? You can see the data width because you are doing the same operation on A1 with B1, A2 with B2, and A0 with B0. So here you will have a packed array of A0, a packed array of B2 to generate the corresponding result. So again, it's not correct. You should have shown here. Are you getting this? How it works? Same instruction, but a pack of data. So how many additions here? How many addition here? Because finally you have to add the correct. You can say that these are corresponding elements of, let's say, two strings or two arrays of 1 by n. Okay. So there are many such cases where this will be useful, and this is the concept that is primarily used in GPUs. That GPUs actually are graphics processing unit. Imagine this, that you have a screen this big, and if there is only one processor to do something, let's say MPEG decoding and show 30 frames per second, then it has to have the entire stream of so many pixels. But you can divide it into tiles. Suppose you have 100 processor available to you. Okay, you can divide it, let's say, of 25 by 4. So each is taking 1/100th of the screen, but the transformation is same because you have pixels to be transformed which are independent of each other. See here you would notice that there is no connection between B0 and B1. They are independent. But this is a pair. So like this, there are many situations where SIMD can be used, and the instructions look like this, that instead of having a standard integer register, you have a register which you can use it, let's say, for integer operations at the same time. So what will happen is it will divide it into 4 virtual registers, sort of, and corresponding A0, A1, B0, B1, like this. Okay, so these instructions are called as SSC. Again, what happens is the compiler will take advantage of this if you tell it to do this. You can identify that my data is SIMD, or there are like codecs available on Intel processor. What is codecs do? They will take, codecs is coder, decoder, codec. So MPEG-4 has a codec, MPEG-3 has a codec. So these are written in software. So this is how SIMD works. Now coming to the multi-core part, which would be of significance to you. So first is that you have a CPU core which has pipeline, which is superscalar, in which there are SIMD instructions. So whatever I told you, the 3 things, they are already there inside a CPU in a core. Now what you do further is to make instead of one core you have 2 cores. So the entire CPU is duplicated, having pipeline, superscalar, and SIMD instruction. So this is like having 2 separate CPUs, which has its own private cache. Because what is a cache? It's a fast memory which is connected to a core. So if the data exists here, it is executed at the fastest possible rate. But this size is small. So what they do is they also have a L2 cache. So I will not get into cache architecture, but there is hierarchy. This is fast and small. This is bigger but slower. And outside that is so this is inside one chip. In this case, you have 2 cores. Similarly, you can have 64 cores, or having L1 private cache, L2 can also be private. So you can have in some CPUs L1, L2 caches are private, and L3 cache is common. So any data that both the cores want to use is kept here. L2 cache, any data that they want to use individually, it is typically kept here. So this hardware manages. You really don't have control over it except that the compiler can do some optimization steps. So now this connects to the external memory. So how does it look like? That single with 2 or more, each unit is a core which is like a complete sequence, which can take its own set of instructions. So this you can see is an MIMD, multiple instructions, multiple. Now taking it further, so inside one CPU, you will have this kind of thing, multiple. So now how it happens on a node, so you'll find that the main memory is here. Remember those blue sockets that I mentioned? So that are common to all the cores. So any data that is to be used by all the cores across all the CPUs, that will be typically. So your algorithm can first get the data here from wherever it is, home area somewhere, and then distribute it to the each core. So that is the way it will work. See, you will find that L1 cache here is fastest, L2 is slightly slower. This is very slow. Why? Because in this case, 4 cores are trying to reach it. If it's 64 cores, 64 cores are trying to reach it. Your program will run fastest if it is such that each core has its own data available at the nearest place. But these sizes are limited, so you have to fall back on main. Where does data come from main memory? It will come from the NFS, the hard disk, which will be the InfiniBand or PermNet. So like this, there is hierarchical data. The data resides in the NFS, that is the starting point. From there, first program runs that distributes the data. So parallelly, data can be fetched by each node. And once the program starts, the hardware manages the data that is frequently needed by bringing it in the cache. So that is how the multi-core architecture.
The main memory is typically called RAM in PC.
Right. That is that you call it at random access memory like DDR5 and all that you get 128 GB and so the blue sockets that I showed that contains the memory. That's a DRAM.
Those are RAMs.
RAMs.
Sir, Lakshya you told me. Lakshya.
Cluster. That is a parallel file system. I showed you the components of the supercomputer in which there was on the right hand side corner the array of hard disks. So those are used while the program is running. They will generate data. That data will not fit in here. That data will not fit in here. It will go to the hard disk. Because you are, let's say, taking a chunk of data, processing it, putting it back. Like this. Okay, so going back, just a recap. The multi-core CPU is here, the main memory is here, and the white sockets contain the parameter or InfiniBand card, which connects to the cluster file system from where data in out can take place. That is how the whole thing works. Okay, so why do we do it? Why do we do all this jazz? What is might make it complicated? That is because we are trying to overcome the limitation of a single CPU system. So what are the problems? First is sequential systems are slow. Okay, each CPU is running at a certain frequency, so that it has its limitation. So if you are running a sequential code, because it is slow, it may take days, weeks, maybe years in some cases. However, we said that more CPUs, job is divided among them, so you will get it done faster. Second problem is they are small. Means you would know that every CPU has certain address lines, 32 address lines. With 32 address lines, 4 GB is the maximum memory you can support. So if there is only one CPU at a time, only 4 GB of data will be available to the rest of it is an hard disk which is slow. But if you have let's say 10 CPUs, add them, so 40 GB of data can be brought in. So what are we doing? We are saving time. We are also solving working on bigger data. So that is the reason why we move from sequential systems to parallel systems. Okay. So now, how do you? I already said this. How do you make use of the system that you have like this? First is that you have a team of domain expert and computational experts. Only domain experts cannot do it. Only computational experts they are good at mapping algorithms to the hardware knob. But what are the algorithms? Which are the efficient algorithms? What? How should the problem solved in the environment be? That is all decided by the domain expert. So you need a team. Like you can see that we have bioinformatics team of let's say 40 members. Out of them, 20 are domain experts, 20 are computation. Together, they deliver a product. So you have when you are designing a HPC aware software, you have a software that has to run on HPC system. You have to start with the parallel algorithm. Thinking parallel is the first step. Which part of that algorithm is parallelizable? If there is no part which is parallelizable, please don't consider it for HPC system. This is the first test it has to pass. That there has to be some mechanism where each problem, small problem that we have, can be assigned to a particular process. Then you have to convert that algorithm into code, and that code will make use of parallel programming frameworks. I will explain that three of them in the slides to come. So that is at the application level. And how do you make use of other option is, one is you develop. You are a research scholar. The problem that you are solving is no software for that. You would be interested in developing a application. Otherwise, there are some open source things like NAMD and so many of them. Every field has OpenFOAM, has CFD domain. So they are already there. So they can be used, or something like ANSYS, but they are costly. And ANSYS and all, they will say how many CPUs they have, they will charge it accordingly. So that is the way one would make use of HPC. Now there are some standard paradigms in the algorithms that you can employ. So in ideal situation, once the parallelism part starts, it should be every processor has unique work to do, which means that it has its own data, it's working on that, and the communication among the processor is unnecessary, which means that there is no time that is spent in communication, all time is spent in computing, and this is ideal that all processors do equal work. So they start together, they end together. But in real life, it will not happen. It's going to be imbalanced. Some processor will do it as a lesser task, some processor will have more tasks. So you have to synchronize. And that is where the algorithms come in. I will explain each one of them. So one is called as phased parallel. So in this case, this is called as a super step. What is a super step? Compute and synchronize. So here, before compute starts, the workload is distributed, and ideally they should take equal time, but they will not. One of them will finish first, one of them will finish last. So till the last one finishes, the first one will wait. There they will exchange the data whatever they want. Because then the computation can proceed independently, and then like this you keep doing this, and at the end you have the so compute part, communication part, and what they do is if there is some data required, then while this compute is on, the network will get the data and keep it ready for the next phase. So that is how this pattern works. Then comes divide and conquer. The grandfather starts the process, gives it to children, children give it to grandchildren, half the one. Grandchildren complete and give it to fathers, father give it to grandfather. So there are certain algorithms like quick sort. It has got a certain number of data which has to be quick sorted. You have two children, divide it among them, they will sort and give it back to you, and then you can put them together like this. And the pipeline model, this is good for streaming data. That is, you are getting continuous data. So it's very similar to the pipeline that I explained for the hardware. So one set is processed, given to Q. While that processes, Q is to R. So while Q is processing the second set, first set, we will get the second set. When R is processing the first set, Q is processing the second set, P has read the first set. This is useful when you are streaming kind of thing. Data is coming in real time, you are processing as it comes and goes. Other is process farm model, which is similar to the this model, except that you have only two levels, one master and multiple workers. The example that I gave in the morning, 1000 processors, one master and 999 workers. So each one of them gives the task given to it and returns the output to the master. Then there is a domain decomposition. So this is useful for matrices, multi-dimension matrices and all. Again, this is what I am telling is in theory. In practice, we will have a combination of these. And these are some of the representative things that I have mentioned. You can design something of your own. A combination of this which best suits the data that you are going to process. Okay, so the algorithms that you are going to use, which are parallel in nature, there are four attributes which are very important. If you don't have them, then these algorithms are not suited for HPC. First is concurrency. I think I don't have to say anything about it since morning we are talking about parallel, parallel, parallel. So concurrency has to be there, basic qualifying criteria. Then scalability. The algorithm should be such that today you have 10 processor, you should be able to scale. Tomorrow you get 100, you should be able to divide it 100 and do it. But there are some algorithms that reach a plateau after a certain number of processes. Like beyond 1000, you will not get any gain because inherently the algorithms are like that. So this is again a desirable output. In practice, you will have to see how what best, how far you can scale it. There are some algorithms that are termed as embarrassingly parallel. That means any number of cores you add, you will be able to do it. Like that, finding the biggest one. Any number of yours data size increases, number of processor increases, the thing that one processor has to be so well defined that any number of processors you can add, it can consume the data that is given to it. Then data locality, I explained to you with reference to the caches that if the data is available with the node, you can tie it up to the node, then you don't, as you mentioned, if you go to main memory, if you go to the main file system, it is going to cost you in terms of time. So try to make sure that once the data is with you, as much processing you can do. And finally, modularity. This is applicable to any software you are developing because debugging, upgrading, fixing problem becomes easy if your program is modular rather than monolithic single. Alright. So typically when you write a construction of a typical parallel code is there is one process that starts initially that distributes data to the memories of the respective nodes. It also distributes the respective code to the processor, which may be same or different. Some codes may be running the same program because it's you are dividing the data. Some code processors may need a different code because you are running a different module on it. Then you have organized, synchronized the workflow, one of the parallelism paradigms that I mentioned. And once you get the thing running correctly, then you can optimize the resource requirement through efficient algorithms, coding that takes optimizing compilers and many other things are there, which some of those things will be explained to you during the hands-on session. So, what are the frameworks that are available? Two of them which will be covered is OpenMP and MPN. OpenMP is for shared memory computers. Like you have a laptop which has got 8 cores, OpenMP will work on it. Or if you have a node with 32 cores, OpenMP will work on the node. It cannot go beyond the node. If you want to go beyond the node, then you have to use MPN, that is distributed. So in real life, you have programs that is a combination of OpenMP and MPN. So within the node, you will use OpenMP. Across the node, you will use OpenMP. But that's an advanced programming practice. All the commercially available software, all the open source software which are perform well, they all use a combination of this. And with accelerators coming in like GPU and AMD and Intel, they are making accelerators. OpenSCC is a one that you have to use. So this is OpenMP and OpenSCC. They are compiler directives. Means you put hash pragma something and tell the compiler to parallelize it. Whereas MPI, you have to link it with the library. This will be told to you how this is done in the subsequent lectures. So OpenSCC they may not cover, but these two they will cover. CUDA some part, one of the persons from NVIDIA will come and tell you about the CUDA part. But CUDA is different than OpenSCC. CUDA gives you better performance. OpenSCC gives you faster change. Like you have a serial code, just insert the directives and you are able to parallelize. Finally, I have taken enough time, so time for summary. What we said is that the application that I told you, you find that it's actually being used in our day-to-day life, but common people do not know. Possibly you also did not know about so many applications of HPC today. You got to know, and the fundamental technique, parallelism is a fundamental technique. Without parallelism, there is no HPC. And when you want to scale up the performance, you want to solve bigger problems, you have to have appropriate communication network and software stack that allows the problem to be divided into so many of them and together. It is, if you have seen any symphony where there is a conductor and there are so many performers, they all work in sync. That's how you get a symphony. Same thing happens here, that all the nodes have to work in symphony. And what was found was still few years ago, before GPUs came in, number of CPUs were increased and the cores were scaling up. However, now accelerators are coming. CUDA, OpenACC, these frameworks help us in. It will told to you how those cores works, what are their positive points, what are their limitations, that will all be told to you. And finally, you have what we began with teaching here is us. So mathematics algorithm is what is driving the whole thing, and that if you are good at that, then it's easy to conquer it. So with that, if there are any questions, I will take them. How much time do we have for the clocks? Oh, just a
Given that all these architectures and the algorithms are similar or functionally similar, then what differentiates a top 500 from a supercomputer from the top towards the bottom? Is it hardware or the algorithm or?
so see, as I mentioned, when you want to rate a set of computers, okay, the metric has to be same, and that software is same, which is HPL. So HPL is the software that is rating them. Okay. So now all of them will have a similar architecture, either a cluster. 99% of them have a cluster. See what happens is the hardware is on top of that you put a layer such that MPI should be able to run. That is the requirement because the program HPL is based on MPI. Alright. So as a result, what to answer your question, they will have different number of processors, less number to more. You can check that out. But two things matter in that: the compute part and the communication. These are the two important attributes of every HPC system in that 500. And the combination of that delivers the performance. So one of the things, if you go through that chart later, you will find that they have written the number of processors that they have, how many cores they have, so that they will find that they are increasingly from 500 to first, the number of cores increase, but it is not in proportion. Sometimes a processor with system with less number of cores has a higher rank. That is because its communication and the architecture, software architecture is better. Okay. So the thumb rule is as the number of core increases, the performance increases, but number of core is not the only term.
So what is the limiting criteria or limiting parameter? We cannot extend the number of cores to a suppose infinite number of cores. If I want to have a supercomputer, I just put on number of cores more than the frontier or the mentioned. What is the limitation?
Limit answer is little clear, but the answer is money. I hope you got the message. You can theoretically you can keep increasing any number. Just have a network that scales up, and the networks are such that you can have multiple layers of. But what will happen is the performance you get for the price that you pay will not will settle.
Is there any role to play of this communication?
Of course, they will saturate. So theoretically it will run, HPL will run, but after a certain point, the returns will diminish. The law of diminishing returns is there in economics and applies here.
Any queries from online participants?
No, their chance is over. Anybody has raised hand?
No. Let us know.
So Chandan Sarkar is your student. Chandan Sarkar is your student. Chandan Sarkar. Is he still here or not? Ah, fine. Harish. Ask him to unmute.
Arishit, please go ahead with your query.
Hello, am I audible, sir?
Yes, you are.
Uh, nice presentation, sir. Sir, can you please briefly mention about how hyperthreading works in case of parallel computing? When you show the architecture of the core, you show how the memory is shared and how things works. But in modern processor, they always come with hyperthreading, right? So,
So what happens is when you enable the hyper-threading, the CPU tries to make sure that all the cores are running all the time. Okay, so by hyper-threading, on every core, see typically what happens is when a program is running, for some cycles, some of the cores may be not used because it's waiting for memory to get data or hard disk to get data. In such cases, hyper-threading allows to basically if you have a single core, hyper-threading makes you look like two logical cores that are available to you, and that it tries by having two threads in the memory, it tries to optimize the usage of core. However, in case of HPC system, we try to disable hyper-threading. The reason being the upper layers, the code that you have written should be able to saturate the codes. So though hyper-threading can be enabled, but at least in HPC system, we try to disable it. You have a very good question, but because hyper-threading is typically has to be disabled because the compilers and other upper layers should be able to keep all the cores busy. There should not be need for hyper-threading because hyper-threading has its own switching overheads. So that we want to avoid. We want to make the all the cores being used by the programs through the program itself, not by the hardware, which will switch the two threads. Does it answer your question?
yes, sir. Yes.
Okay,
Thank you.
thank you. Next question is from next. One last question. Maybe okay. I show my email address Ashish A@cdac.in. I think we didn't reach that part.
Sir, I stopped the sharing.
Huh. So Ashish@cdac.in. So you can send me questions here. One question we have to read.
Anirban, can you go ahead with your query?
Anirban, you can unmute him. He's allowed. My mic is on. Don't touch it. His mic you have already unmuted. No, disable mic आ रहा है and enable किया है तुमने already. Allow mic. क्या था?
Anirban, can you hear us?
Anirban is muted. He has to unmute himself first. Anirban Mandal, are you there? Maybe you can send me over email. Right. I hope it was, I mean, understandable and you got a flavor of what to expect in this.
Thank you.
Thank you.
Sir, I request our head to
Yeah, so we should take a photograph with him and also can you somebody can stand here and take a picture? My camera is not.
You can take with my camera because I want it.
I think you did that.
Yeah.
There is a point setting for that.
Okay. I think it's everybody's coming, so just click once and check.
Can take it. Yeah, can take it.
Okay.
Somebody is close in my
Right. That is all. Okay.
Thank you all.
Thank you, sir.
Break for lunch.
Immediately.
Yeah.
So then I think it's a very so try to finish your lunch by 1:30 we'll start the next.
So the lunch is arranged in ground floor. So if you go ground floor on the right side, you can see there is a big room. where lunch is arranged. Please take your lunch and please be here back into this room. For 1:30, when we start the next meeting.
recording